This question tests your understanding of the TweedieRegressor and its power parameter. I'll help you understand how different power values map to different probability distributions. We'll focus on which distributions are suitable for modeling insurance claim costs, which are always positive and often show more variability than their average, overdispersion. Let's check this out. A power of 0 means we're using a Gaussian, or normal distribution. A normal distribution can have negative values, but insurance claims can't be negative. Therefore, this statement is incorrect. Power of 1 uses a Poisson distribution. Poisson distributions are great for count data, like the number of claims, but they assume the average and the variance are the same. Insurance claims often have a variance much higher than their average. This is overdispersion, so this statement is also wrong. Here's where things get interesting. A power between 1 and 2, like 1.5, gives us a compound Poisson gamma distribution. This is perfect for overdispersed count data. Precisely what we might see with insurance claims. The variance is allowed to be higher than the average. This statement is correct. A power of 3 gives us an inverse Gaussian distribution. It's perfect for modeling positive, continuous values, like claim amounts, with overdispersion. This matches our insurance claim data characteristics. So, this one is correct too. I'm exploring the Tweedie distribution family, a flexible class of probability distributions used in statistics. It's really useful because it includes several common distributions, all linked by a single parameter, the power parameter. Let's dive in. This is the key to understanding the Tweedie family. It determines which specific distribution within the family we're using. Different values lead to different distributions with their own unique characteristics. When the power parameter is 0, we're working with the normal, or Gaussian, distribution. It's a classic bell curve, but remember, the normal distribution can have negative values, which isn't always suitable for things like insurance claim costs that must always be non-negative. A power parameter of 1 corresponds to the Poisson distribution. This is excellent for modeling count data, but it assumes that the mean and variance, spread, of data are equal. For insurance claims, where variation often outpaces the average, this may not be the best fit. Here's where it gets interesting. A power parameter between 1 and 2, inclusive, gives us the compound Poisson gamma distribution. This is especially useful when dealing with count data that is overdispersed, meaning the variance is larger than the mean. This is common in insurance claims, so this distribution could be a great fit. I'm explaining how the power parameter in scikit-learn's TweedieRegressor impacts the type of distribution used to model data. We'll explore different power values and the associated distributions. This is crucial for accurately modeling things like insurance claim costs. Let's dive in. I'll analyze the incorrect answers. I'll explain why certain choices about the power parameter are wrong given the context of insurance claim cost modeling. We'll examine specific incorrect assumptions about the distribution types and their suitability for this scenario. Think of it like a detective game. We're weeding out the wrong suspects. I'll clarify the correct answers, explaining why those choices regarding the power parameter are suitable for modeling insurance claim costs. I'll focus on the properties of the chosen distributions and how they match the characteristics of non-negative, possibly overdispersed claim cost data. These are the right fits. I'm going to explain how the TweedieRegressor in scikit-learn uses a power parameter to choose from a family of distributions. This is important for modeling things like insurance claim costs, which are always positive numbers and often have more variability than you'd expect. When the power parameter is 0, we use a normal distribution. The normal distribution can have negative values, so it is not suitable for modeling insurance claim costs since those are always positive. If the power parameter is between 1 and 2, you're working with a compound Poisson gamma distribution. This is great for situations where you have overdispersed count data. That is, when the variability is higher than what you'd usually see for count data. Insurance claim costs often fit this description. A power parameter value of 3 indicates an inverse Gaussian distribution. This distribution is useful for positive, continuous data that shows overdispersion, meaning the variance, spread, is greater than the mean, average. It's another good choice for modeling insurance claim costs. With a power of 1, you use the Poisson distribution. The problem with using this for insurance claim costs is that the Poisson distribution assumes the average and the variability are the same. However, insurance claim costs typically have more variability than the average, so it is not the best fit. The power of 2 gives you a gamma distribution. This works well when modeling positive continuous data where there's overdispersion. I see that you are interested in the Tweedie distribution family. It's a really cool family of probability distributions. I find it fascinating because it connects several well-known distributions using a single parameter, the power parameter. Think of it like a toolbox containing different tools, distributions, and the power parameter acts like the tool selector knob. You can choose the right tool, meaning the right distribution, for your specific problem. When the power parameter equals 0, you get a normal distribution, which is famous for its bell shape. It's symmetrical, so the data is equally spread around the mean. This is perfect for data that isn't too skewed. With a power parameter of 1, you obtain a Poisson distribution. This distribution is useful when dealing with counts, how many times something happens. For example, how many car accidents occurred in a given month. The catch is that Poisson assumes the mean and the variance are equal. That's not always true in real life, like with insurance claims. If your power parameter falls between 1 and 2, you are working with a compound Poisson gamma distribution. Think of this as a more flexible version of the Poisson. It's particularly useful when you deal with counts where variance is more significant than the mean, a situation often seen in insurance claims, overdispersion. A power parameter of 2 gives you a gamma distribution. This is used for modeling strictly positive continuous data. If you're dealing with values that are always positive and are skewed, the gamma distribution is an excellent choice. Again, think of insurance claims. Their values are never negative. Finally, if you set the power parameter to 3, you'll get an inverse Gaussian distribution. This is also used for positive continuous data and has a property similar to the gamma distribution. This is the title of the quiz. We will explore how the power parameter in scikit-learn's TweedieRegressor impacts the type of distribution used to model data. The power parameter of 0 means we're using a normal distribution, or Gaussian distribution, which assumes data can be positive or negative and follows a bell curve. It's not suitable for modeling claim costs, which are always positive. Setting the power to 1 gives you a Poisson distribution. This is used for count data, such as the number of claims, where the average and the spread are equal. Insurance claim costs asterisk, however, often have a larger spread than the average, so a Poisson distribution isn't the best choice. Power between 1 and 2, like 1.5, uses a compound Poisson gamma distribution. This one is great for situations where you have count data that's overdispersed. That is, the variability in the data is higher than what a standard Poisson distribution would predict. This perfectly suits insurance claim costs. This is a key correct answer. With a power of 3, you get an inverse Gaussian distribution. It's used for continuous, positive data with high variability. This is another correct answer, suitable for modeling insurance claim costs. This quiz tests your understanding of the TweedieRegressor in scikit-learn, specifically focusing on how the power parameter affects the type of distribution used to model data. I'll help you understand each option. This question asks you to identify the correct statements about the relationship between the power parameter in the TweedieRegressor and the type of statistical distribution it uses. Let's examine each option to see which ones are right. A power of 0 means we use a Gaussian distribution, also known as a normal distribution. However, this is incorrect for modeling insurance claim costs because Gaussian distributions allow for negative values, but claim costs are always positive or 0. A power of 1 corresponds to a Poisson distribution. This is a distribution for count data, like number of claims. The problem here is that a Poisson distribution assumes the mean and variance are equal, whereas insurance claim costs often have more variance than their mean. This is called overdispersion. Thus, this is also incorrect. If the power is between 1 and 2, inclusive, we use a compound Poisson gamma distribution. This is perfect for overdispersed count data, meaning when the variance is larger than the mean. This aligns well with how insurance claim costs often behave. So, this is correct. The power of 3, we get an inverse Gaussian distribution, not gamma. This distribution works well for modeling positive continuous data with overdispersion. This fits the characteristic of insurance claim costs nicely, making it also correct. Based on our analysis, you should select options C and D.